Okay, it's beeping. That's okay, fine. So today I'll talk about graphene, and I would like to review a bit the tie binding. On Monday we'll discuss the course, the midterm, in detail, really in detail. On Tuesday we'll do something else, but I will still review a bit the tie binding and electron models to kind of repeat a few times. So, the tie binding method. Why do we care? Why do you guys want to study tie binding?
I think we study tie binding because at times the free electron model fails to describe the bond structure of some materials.
Why do I care about free electron?
Why do you?
Why do I care about the free electron model? Why do we care?
We want to study the electronic properties of material.
Okay.
Through the knowledge of their band structure.
Okay. So our ultimate goal is the band structure. That is to know the energies of the states, to know the wave functions also, how they look like. And what do we learn from there? I realize from the quiz that you are not very familiar with the band structure yet. What do we learn from there? What can you learn? What else except the energies?
Classify whether they are metal or insulator.
Do you all know how to classify the metal from insulator?
Metals, yes. Metals, yes. But we don't see any metals and insulators. No.
No metals. Okay.
The
Michelle,
metals,
you are talking about advanced things. Yes.
The metals, yes.
Yes. Okay. It is not true for everyone, unfortunately. We'll discuss on Monday about the metals and the. So you had two different methods so far: the free electron and the tie binding. They're the limiting cases. Almost everything you will ever have in your scientific life will be in between. But there are some, very comforting points. If you look how the band structure, how the band dispersion at gamma looks like in the free electron. In tie binding,
Cosine,
the typical thing is cosine, no? I'll make it minus cosine. So it will be cosine and like this. No? It's very comforting to see that. Because here, if you expand around small k, it's virtually the same. And indeed, in real life, you will see at the gamma point, they all have this kind of dispersion. Then it changes, depending on the crystal structure and everything. But if you have the two limiting cases being so similar, I'm quite happy, because everything in between cannot go very far from there. So this is a comforting idea that I can say something of the simple cases, which I can do by hand almost, but I can say something, predict or expect, even in the more complicated cases. Okay. So for the free electron, we use the free electrons. Oh, simple. For the tie binding, we are using what basis?
We are using specific atomic orbitals and
the chosen ones, which we choose. So
sorry?
you notice the ones we choose, the atomic orbitals we choose.
Lower energy atomic orbitals.
Meaning they are completely opposite. These are localized in space.
Localized, yes.
They are non-zero in only a very particular small portion of space. They are non-zero. While you have plane waves which extend everywhere. So you really see there are two complete limits, furthest limits. Okay, I use Nadia's notes to review the things. You don't have to copy this at all. Just to have it. Okay, this is actually not from Nadia, I think. So I'm first expanding my states in some basis. Then I'm writing this basis as a block state. No? We always have to have block state in a crystal. Always. So, I think in the class you proved it's a block state.
Yes.
I'm not going to go through any of that. This is just a review that you can follow, because graphene can get a bit messy if you don't follow what you're doing. Atomic, mu I. Okay, so what Nadia did, she did the most general case, which might be a bit confusing in the beginning, but you have it all. Now you can use it for anything. So, R, what is R?
R is the Bravais lattice vectors.
So it goes over the whole lattice. Good. Am I missing something? What is the mu?
Mu is the index for basis per lattice. Like when you go to lattice, you want to go to different
So
basis.
if I have, let's say atom BCC iron, what is mu?
The what?
I have BCC iron. Iron in BCC lattice. What is mu? BCC.
No, it's
BCC.
It's
BCC. I'm asking BCC. It has one atom.
one atom.
You can describe the primitive cell with one atom. Okay, primitive cell is a Bravais lattice, no? With one atom. So it's just one. If I tell you cobalt hexagonal,
I should be
it should be two. Huh? You understand how it works in the real life. So very often you will have just one atom, and this is one, this goes away. And then this also, this is like the vector in this basis, how you have to shift it to come to all the atoms in the basis. That might not exist always. Okay, and then I, what is I?
I is for orbitals. Once we go to atoms, so
The levels, no, okay. In atom you can also say levels, yeah, fine.
Yes.
How many I's can there be?
Infinitely many.
Depends.
If it is a bounded state.
You talk before everyone. I want to see if also others understood. These are simple things, but you should have them clear, that you know what you're doing. Fine. So this is atomic functions. What is our Hamiltonian? I'm copying, so no need to copy it from the blackboard. There's a small v, u, atomic. Okay, the same one. Okay. So this V of R, the capital one, is the sum of all ionic potentials. Sorry. The small v is at one atom. No? So I can write it like for any atom. The tissues. So for any atom, I can write it this way. I just took one particular atom, and it's an atomic potential. And this part here will form my crystal field. At a certain atomic position, placed in the lattice, this will mean the potential of all the other atoms surrounding. Okay. What does influence this potential? What it will depend on? So I'm here and I feel my neighbors, maybe second neighbors. What can vary? What is determining what I will be feeling? Do you understand what I mean?
The structure of the crystal.
The symmetry. I don't think you'll have symmetry course, which might be useful actually. So this part, this is the crystal field, depends strongly on the symmetry. This is where the symmetry of the crystal enters. And this is atomic energy. Yeah, I have this bad habit of writing energy this way. Well, Nadia is writing it this way. I'm really sorry, but I don't think I can keep it. I'll switch. Now I will try to do her way, but in the lecture I'll switch to normal capital E. Sorry for that. And Okay, let me just write something else. Then you get the circular equation, which is very messy, but that's the one you need to use to solve actually. I mean, you don't have to, you can go always from here. But it takes a step or two more. Principle, you use circular equation to solve the problem. This is K. This is the energy, K dependent. This is all from your notes. I took from her notes. So. And then let me also write what this is. This will be atomic levels. Okay, let's write the K up. Plus the mu I prime, mu I. Okay. Okay, and we still have to expand to write everything. I think it's worth it. It's a bit of repetition, but because I hope that you will completely follow the graphene example. Completely. I mean, everyone in the class. It's easy. It's nothing special. So that's why I want to make sure that we review everything you need. If you have no time to study, that you can still do it. So now we want to put all the indices right. This is this crystal field potential. And the atomic. These are the overlaps of the orbitals. We normally take them to be zero with the neighboring cases. No? So this will be, it was 5, I have it, yeah, 5 mu I prime. Normally as delta mu I, E prime. Doesn't have to be. Why? Because we assume they are localized. No? So you have different sites in the lattice, and if they are so localized, the atomic functions are not going to overlap much. Because we start from the idea they are localized. So it's not a big assumption, it's not a huge mistake that we are making there. So, so in this side, you will essentially get just this, the eigenvalues times the coefficients of this expansion. On the left side, you have, this is again delta mu I. You have atomic level, and you have the hopping. The hopping is using this crystal field potential. And did I miss anything? No. So what can you tell me? You have atomic level, and then this hopping. Will the energy in the end be higher or lower than the atomic?
Lower.
Does everyone see it has to be lower? Tell me the physical, okay, not you. Tell me the physical reason why it has to be lower. So, atomic energy is what you have levels in the atom. Now we put these atoms in a crystal, and they have neighbors. And this term here comes from the interactions with neighbors. Just with the neighbors. It's just the potential. I mean, you have a lattice. It's just what this atom, let's say this atom, feels the potential of all the neighbors. So it's the influence what others are doing to you. In a way, I'm just talking very not scientifically.
Then it will be lower.
It has to be lower.
Yes.
Why?
Because I think we take the crystal potential to be an attractive potential, so it's a negative term.
Okay, this is a mathematical explanation. But the simplest thing, if the crystal is bound, it means that binding with, into a crystal is lowering the energy. It means that the interaction due to neighbors is going to be lower than the atomic. No, it's very intuitive. This is okay, mathematical way, fine. But it has to go down. Okay. Oops, this review took a bit longer than I thought. Okay, then I maybe can skip the rest. It's not number one today. I'm really bad. Last year we had no chalks, you know. We were going around for chalk this high, and oh, I found one. So this year, like, we are richer. Fine. Any questions on this? Okay, let's do graphene. What do you know on graphene?
Two-dimensional material.
Please speak up. Turn to the blackboard and I cannot hear so well. So.
Just a single thing.
Okay. Now the drawing. I'll do my best, but okay. The past shows that it's not very easy to draw on the blackboard and started badly. Yes, it's a 2D material in which crystal structure? No. It's not hexagonal.
Triangular lattice with two bases.
Okay, yes. Or also known as
Honeycomb.
honeycombs. So, mamma mia. It's much easier on the paper, I assure you. One's a bigger, one's a small. Right, so the atoms are here. How did I put names? I should copy the same. So we have two atoms in the basis, no? A and B. I gave some names 0, 1. I will use it to count all the terms, so it's important that we have the names same. Okay. I just give these names, it's nothing official, just for the lecture to be able to follow. And it has primitive vectors, which I can define this way. A1 and A2. No, I think A1 is down one, yes. Fine. Good. You can do it better in the notebooks and the notes. Carbon has 4 valence electrons. Carbon. So it is first level 2s, second level 2s. Just a second, did I? No, it is 6. What am I saying? 6. Yeah, actually correct. Yeah, valence are 4. Right. Good. 6 electrons, 4 valence electrons. And carbon is known to have many different structures, and they depend on so-called hybridizations. How these orbitals. So this is chemistry. I know Nishan hates chemistry, but this is something known I mean, in general, in physics, we also use it. So, you know, graphene, as I'm showing now, diamond, it's a 3D structure. Diamond has, for example, something known as sp3 hybridization, 1s and 3p. In graphene, it's sp2 hybridization. So let me draw it properly. So we have 3 sp2 orbitals, which means 1s and p. Gives you 3 orbitals of this shape. Okay, this is not drawn so well, I will erase it later. But they change the shape, and they actually happen in plane. You will have something like, I'm just trying to, so you have one of these sides going, and it has this kind of orbitals in plane, which are extremely, extremely strong, meaning that the energy is deep. This is one of the hardest materials. Last year I had to give some outreach, I did an outreach talk in a bar, and I chose graphene. It was like a pint of science. They make us go to the bars at night and talk. And I talked about graphene, and I looked a bit about into Nobel. Graphene got Nobel Prize. I mean, people who wrote. Yes. And I looked in what they wrote in this report on the Nobel Prize, and they actually drew in the Nobel report, drew a hammock with a cat inside, saying this is such a fantastic material that it is so hard that 1 meter squared of graphene sheet can hold a cat. If you could make a sheet that big, which is hard to produce at the moment, but it is so hard. So it is these sp2 bonds, which are extremely, very, very hard to break. So they are deep in energy. That's my point. I don't want to describe them. They are very deep. They won't be broken by anything. But what is left is 1 pz electron. So plus 1 pz electron. This pz means it's out of plane. So plane is always xy, z is perpendicular to the plane, and it will be, okay, this is too much in the plane. If I draw it like from the angle, like you will have these in plane, and then 1 pz orbital, this one going out of plane, and this one will actually bind possibly to some odd species or whatever. And this is the one which will be responsible, it's the valence state, for the particular properties are close to the Fermi energy, about which you probably know or there's something, but we will derive, because graphene has a very particular dispersion. What is dispersion, you know? The word dispersion, I know you know. Dispersion is how the energy changes in the k-space. Okay, good. It's good to say such things, it's boring for a few, but fine. Okay, now let's write the A1 and A2. So this is 120 degrees in honeycomb, in any like this triangle. So this must be 30, both of them. This is the degrees. I can express x coordinate. Will be cosine 30. And the y will be negative sine 30. And symmetric thing for the other vector. Okay. fine, everyone. Then I will switch my origin here to be able to define better these D vectors in the basis to have them symmetric. So I'm switching the origin to here and moving these vectors by half. So they remain the same, I just move the origin. And I call this minus D and plus D. Oops. How much can you see? Not much, I guess. Plus D minus D. Did I use the same here? Yes, good. So the atom A will be at minus D, the atom B at plus D. B at plus D. Fine. So I can express all the vectors. A2 plus minus D. All the atomic positions. Fine. So far, all easy. And it will be easy all along. So you shouldn't get lost. If you get lost by anything, there is no reason to be lost. I was too fast. We'll repeat it and okay. Now let's write the block function. So it is going to be P is electron. I'm describing that it's good to know what you're doing, to keep in mind what your real goal is, not to just become mathematical and you do mathematics forgetting your goal. So, and this is, okay, all the R vectors from the phase factor. Okay, and this is the okay, this is enough. Just what we repeated already, reviewed, nothing else. But now let's expand in this mu. Now we have A and B sides. A, phi plus C plus A, B, okay, A, B, phi. So this is minus D, this is plus D. Nothing smart. To make it shorter, the notation, I'll call this A state and this B state. Just calling it to a bit reduced writing. And everybody's following so far, no? We write the Hamiltonian. A sum, or R, obviously. B or R minus R plus D. I mean, these two atoms are identical. This you never should forget. So I'm only using that a bit when writing. Having it from the world from the place A is just the same as the world from the B position. It's rotated, but it's just the same. Okay. This is my potential R of R and my potential B. They're the same, just rotated in space. But the same rotation doesn't change because it's a symmetry operation of this structure. Fine. Now, of course, this is a sum of all. I can subtract a given potential at a given lattice site, A or B. I'll try to skip that step, not to write the whole thing, but to write immediately to do Hamiltonian. I have to erase something. This I can remove now. Although it's useful to have primitive vectors, so I'll have to use it later. But okay. So I'll start a step before secular equation, but in your problems you don't have to do it. You don't have to go always from there. Just trying still to review. But you don't have to always start from the Hamiltonian and plug it in. So I'm multiplying from left the h on side, which I just removed, and let's see what it gives. So this is the Hamiltonian. I will already subtract the potential at the site I to get atomic part and the crystal field part. I mean, I could have written it there, but to save one step. So multiplying from, I can choose whichever R I want. I'll choose 0, of course, it's the simplest. And let me write minus 3 squared plus sum of R. Okay, I will now add the potential at 0. The A atomic at the 0 position. Plus the sum of these two. I'll call it AR plus VB of R minus V. Let's put R equals 0 not to confuse you. Okay, plus VA. So these are all atomic. I mean, if you want, it's all atomic. Atomic of R equals 0. Fine. Sum of K, AIKR. Put times A. It's a lot of writing, but really nothing difficult. And this shouldn't be in the sum, like that. Here is the big one. Okay. I think it's correct. When you see a mistake, just let me know so that other people at least copy correct. Fine. This we already know what it will give us, atomic energies, and this is the crystal field. I'm repeating the same thing so many times that even if you haven't followed at home, reviewed, you will hopefully. Okay, so multiplying by A state, I have both A and B. No? To make it simpler, I will make it like two different sums. I will call it A with A. No, just that part. This, all this with just the A part. It's simple. It will give us so what do we have? AA and the atomic part. It gives us A, E atomic. And the other part is just lowering the energy. Let's call it delta V R A atomic. This is minus. So this is A with V with A, the second part. Nothing smart. But I have to lower the energy.
Excuse me.
I find the blackboard very small somehow.
Excuse me.
Yes.
But there is like e to the power I k r k dot r while like doing the.
It's just that R equals 0.
Okay,
This is non-zero. This is non-zero only when it's for R equals 0 we
So
chose.
we are just like taking for.
We are multiplying from the left
Okay.
with this state. I chose it. I could choose any, but we chose the simplest one. And I have to erase it. I have a big handwriting, but it's a small blackboard also. In the other room, there is like 4 of them. You can keep exchanging. 1 year it was useful actually. Made it the Hamiltonian. And now it's the A with B. This is a bit more interesting. So I have this A, and I'm looking at all the neighbors with B. This is A, B. I have 3 neighbors. We are normally in the first neighbor approximation, the nearest neighbor. Doesn't have to be, but this is given. So we are using we have 3 neighbors. So the first one is the vector is 0. It's in the same base. So let me write A0 delta VA of R equals 0 atomic with VR. So the 0, 1 term, so let's say it like this, 0, 1, R is 0 because it's in the base. Now I use this part because I will have some R for all the neighbors. But the first one is R equals 0. Let me just write. 0 delta VA atomic of R equals 0 V0. There is no phase factor in front because this is 0. This is 1. R is 0, the whole thing is 1. Fine. So this is 0, 1. Now 0, 2. Now the picture is really bad, but if it was the right picture, you could just do, almost, come on. You could see that to come to this basis, how to say, it's just opposite of this vector. And this one is A1, so minus A1. Almost you can see. So we'll have a phase vector, A minus K, A1. And then the same thing. And the 0, 3 will be the minus, minus this one. Okay. So this is a sum of all these three terms, no? I just kind of wanted to write where they are coming from, so I wrote them this way. You are summing over them. Okay, like this is a bit strange way of putting it, but just to emphasize where they are originating from. Fine. Maybe I still write it again. So, what is this term? How do I find this?
I think we should use some symmetry properties. Are we can calculate this or not?
What is this?
Copy energy.
How do I find it? I'm putting some tricks here. We don't find it in this, but you can do it in a few ways. Some people just take it from the literature. Some do it from the ab initio calculations, calculate these things. I mean, there are a few things. Or you can, in a few cases, even easy cases, try to, I'm not sure. Really, you can derive it. But for us, it's a T. And we will express our energy dispersion in terms of T. So that remains a number. And we know it has to lower the energy, the final energy. So we're like E energy is equal a constant term, atomic term. It has to be minus T, and T absolute positive, I mean positive value. Okay, so what I have, the total one, including the first A with A terms, atomic, minus delta E, plus. This is now AB. We have, in front of this was AB. 1 plus E minus AK 1 plus E minus, this is a bit large, A2 T. And this equals A. Did you all follow how we came to this point? Everyone understood how we reached this point. It's okay? I mean, don't be afraid to ask. I mean, it can be whatever. You just lost for a moment, you didn't follow, and then... Okay, I don't have everything on the blackboard, so it's a bit hard. But this is from the A with A part.
Okay.
And this is from the A with B part. This is just from the hopping, from this part. This was coming with a B factor in front. I don't have it written, it's no space there. So,
That's right.
okay. And now we do again this multiplying each side with b. So it's a bit laborious, this exercise, with b at 0. But I will spare you all the Hamiltonians and the stuff. I will just write the solutions. B with, how did I write it? Okay, just b with, okay, I expressed like that. B0, h psi is equal. B with b will give me atomic energies. Huh? And I'll have a factor b in front.
Yeah.
Ions. Plus B0 delta VB, which is the same, just rotated the other one, of R equals 0. Okay, so here's the sum over R. Here it's AA. I should write AA somewhere. And now let's express, so copying. B with A it should be A. Sorry. So here again, we will have three cases. We have three neighbors of this B. This A, and this A. So it will be 0, 4, and 5. 1, 0. Again, it's in the basis, so R is 0. I don't have the phase. I just have the T part. Delta AB, atomic, AOR. Fine. Then 1 with 4. No, let's say 5 first. There is a phase part. I go from here to here. From this basis to this, it's minus, it's plus A1. And 1 and 4. This is the A2 vector. So again, we have a term, an integral, and phases in front. Do we know this term? What is this? T. But is it triviality? I mean, do you all see it's a T? The same one as this one?
Is equal to 0.
Because here you have left and right term. If you look at it from a mathematical point of view, it's maybe not so simple. But if you look what you're doing here, I mean, they're the same. You turn this way, I mean, you take potential of this one or this one, they're the same. So this is also T. And this is all on camera also. T. And then this term is equal 1 plus E aka1 plus E ka2 T. Okay, but I have to write the full thing. When you copy this, I will erase this to have two equations together. So when you finish copying, let me know.
Excuse me. Up to this point, we haven't actually specified the orbitals per atom. So it's a general thing, we'll put the orbitals there.
Yes, for practical thing. And you would choose something atomic similar to P. No? This is practical choice. We're just coming to the expression in the end. We won't express the wave function, the solution, the eigenstate in the end. It will remain in these phi's, in this. But we will come to dispersion in terms of these T's, which is already a lot. It gives you the shape. It doesn't give you the numerical value, but it gives you the shape, which is a big thing. I mean, this is maybe the most important thing. Okay, so I'm erasing this thing. So we have AB, E atomic, minus delta E, plus FA, 1 plus E, Ka1, plus E, I, Ka2, T is equal A, B, E. Now we have to solve it. We want to find these coefficients. We have two equations with two coefficients, not difficult. And then we can find also the eigenstates. Before that, I will call this, which one I called? Good, I call this one alpha. And this one is the conjugate of alpha. It's so symmetric because we have high symmetry. This lattice is one of the most symmetric ones, very high symmetry. Good. So let me write it. Minus delta E, and here is alpha. Alpha T is alpha conjugate T, and E atomic minus delta E. Okay. This we call it E. All of you can solve this, no? This is not difficult for everyone, anyone. I'll need more space. So you can write this energy here in the determinant. You get this times this minus alpha absolute value times this squared. Times t, sorry. So I'm writing here the solution. E atomic minus delta E plus minus T absolute of alpha. So I already have dispersion. Just I have the problem that the K dependence, which I need, is in alpha. And alpha is here. This is alpha. So I have to find this absolute value to be able to find how my energy depends on K. This is my most important goal at the moment. Okay. Alpha. This is alpha. Here. So to find the absolute value, I find the real part squared, imaginary part squared, and everything 1/2, everything square root. So I'm writing the cosine plus I sine. Cosine, it's an even function, so it doesn't care. Ka1 plus cosine Ka2 squared. Now, imaginary part will be the sine of this and the sine of this. So actually what I didn't say, there is 1/2 factor, which, there is a 1/2 going out, and I separate this into 1 plus cosines, 1 plus 1 plus I sines. Okay, but it's a factor which goes here. Now I see there is a mistake. Sine Ka1. These are both negative here, but this is squared, so I don't care. Sine Ka2 squared, and the whole thing is on 1/2. Good. In this moment, I will construct brilliant zone because I want to draw it along the most interesting direction in graphene, where it's known that there is I can draw it everywhere. From what I have right now, in the approximation of the first neighbors, I have a solution for all cases. Of course, I won't have now time to do it. I'll just go for the most interesting direction, which is gamma K. It's known. And for that, I have to know that K is in the brilliant zone. So I have to construct the reciprocal lattice and brilliant zone. I won't be deriving the vectors. I'll just put the solutions here. It's a good exercise. By the way, you all should be able to draw a brilliant zone of this lattice. So, the B1 is equal to 4 pi over square, and it's equal to square root of 3 a 1/2 x minus square root of 3 over 2 y, and the B2 4 pi of 3a 1/2 x plus. You're welcome to check it. The volume was square root of 3 off, but I can write. So the surface actually is square root of 3 over 2a squared. This is 1. This is 1. So this one is 4 pi over. This I take as the unit. Drawing B1, 1/2 x minus, this is 1.7 divided by 2, 0.8, 0.9. If this is 1/2, 0.8 will be here, 1/2 is here. This should be B1. B2 is 1/2, and the same up, 1/2 is here, 8. B2. I also draw in other direction. Also the sum of these two will go up to here and up to here. And as in any Wigner-Seitz construction, we halve the vectors. So here is 1/2, and draw the perpendicular lines. Okay. It's not perfect, but I've done even worse on the blackboard, believe me. So if you compare the real space lattice and this lattice, they are rotated, by this angle. This is 30 degrees. So it is just the same lattice. This is gamma point, obviously. You're still drawing, okay. Okay, this is gamma, and this is the K point. This is the name nobody expects you to know of each special K point. Don't worry, I know only a few also. And I want to plot along gamma K. For that, I have to know what is the coordinates of K. Obviously, it is in Ky, which is great, but I have to know this length. I know the angle, and I know these B vectors. So I'll go from this, it's a B vector half. I know the angle, I can get this. So let's say cosine 30 will be equal to B vector. It is B1 negative, but absolute value, half, divided by gamma K. The absolute value of B1 is, this gives 1/4 when squared, this gives 3/4, this is 1, so this part gives me the amplitude, 4 pi over square root of 3a. equal this divided by 2 by the cosine of 30. 4 pi 3 or a. Cosine of 30 is the root of 3. Am I doing it right? Yeah. Just to help you.
B1 over.
I forgot 2, no? I'm thinking I'll get something weird here, times 2. Yeah, okay, 4 pi over 3a. Okay, easy to make a mistake. So, coordinates of the k point are 0 and 4 pi over 3a. This is what I wanted. Okay. So this alpha of k equal gamma is equal. At gamma, this is 0. This is 1 and 1. So 3 squared, square root is 3, no? And alpha of k equal k. Let's evaluate that. We are going only along y, so we'll take only the y component of a1, because ky times a1, which is just the y part. So we'll have cosine k a1 is equal cosine 4 pi over 3a times the y part of a1. It was 1/2, no?
Minus 1.
This is equal cosine of 2 pi over 3 over 3. This is 120 degrees. Cosine of 120 is, I think it's minus 1/2. You can just draw it if you're not sure. I always have to draw actually. Minus 1/2. So we have, and for this part, we'll get plus 1/2 a. It's just the opposite sign, but it's a even function, doesn't care with the sign, so they give the same contribution. So we have 1 minus 1/2 minus 1/2. 0. Okay. Now let's see what we get when we draw it. Energy. I will center my coordinate system at this point. So this is E atomic minus delta P, this line. I'm going from gamma to K, the big K, and this is small k. At the gamma, it's, okay, where is my dispersion? It's here, dispersion. I have two values, plus and minus 3, around this point. So I go to minus 3 and plus 3. This looks like 3, okay. And I'm drawing Now, to draw this function is not so trivial. I will essentially just connect a point. But you can use some plotter program. It's not even so difficult, actually. It can be done, but okay. So I know it's -3 here and 0 here. Oops. Yeah, okay. And the same from here. It's actually more parabolic from what I know. Here. Good. We have one valence electron. And actually, if I tell that the band is completely occupied, the valence band, fully, so this is something I know, I can place the Fermi energy just at the filling when the bottom band is fully occupied. You have to know something. It's not trivial just to deduce. But this actually is the Fermi energy also, this line. So we derived the most typical band dispersion of graphene. Because graphene is touching, in graphene, the bands are touching the Fermi energy at only one point. This point here. And what is even more interesting, they are linear around this point. You can actually expand around K and prove it. And this brings almost all the interesting properties why graphene is so much. Because, okay, we'll derive later, the velocity of electrons at the K point is something fantastic due to this interesting dispersion. And it's called semi-metal. It should be metal. There is a band crossing the Fermi energy. But it's just at one point. I mean, it's barely there. You don't have really large density of states. If you should know, density of states will be at the K point. So, I mean, it's just one state. It's almost nothing. It's not like you have many electrons to conduct, but you have something. That's why it's called semi-metal. And that brought a revolution in material physics, science. And if you're interested, we can talk about it. But, okay, any questions on the tie binding, on graphene? We are good in time. Anything? Yes, Chad.
Why is it?
Okay, to really see it, you have to plot this thing. It's not so difficult to get a rough idea, because you're plotting just this from 0 angle to 120 degrees. So you have a sum of two cosines up to 120. It's not so difficult to get it. But if you want to play, you can put it into plotter, and you can also, I mean, if you have now you can get many different function plotters on internet, and you can plot them along any direction if you care, if you're interested. I forgot, I always forget somehow. I'll bring it next time a few papers of ab initio calculation. What is ab initio? It's like when you really take into account everything from first principles and you calculate the band structure, for example, of graphene, and our tie binding to compare with our tie binding calculation, which is the easiest possible, no? I mean, it's done in 20 minutes, in less than 1 hour you can do it. It agrees quite well. And then you can also compare it to other tie binding calculations, taking into account also second neighbors or third. And this dispersion here has very few corrections. So it's valid. So we managed to derive really the most important dispersion of graphene, the most typical. Any other questions?
I just need you to repeat about how to calculate this equal to 0. You say somehow it must
Okay, that's easy. So k equals 0. You want for k equals 0. Okay, this is 0. Sine of 0 is 0. Sine is 0. Cosine of 0 is 1.
I want the other one.
Aha, okay, you showed the zeros. At the K point,
Yes, yes.
Here.
Yes, yes.
so this is what we have. 4 pi over 3a times 1/2 of a.
Yes, I agree, but how do we arrive to that? You said somehow we consider only
K is K, is this, which has only ky component.
Okay, okay,
This is kx, this is ky.
okay.
So I will take only the the y component of a1,
Oh.
which is 1/2 a, and I will multiply the two.
Oh, okay. It's fine now.
It's not. Try to think of these things. You know, this course is not so much about memorizing, no matter what you think about the chemistry part. It's really, we are trying to make you understand simple concepts. They're simple, but for you, if they're all new, that might be a bit difficult. And to be able to apply them, tell how things are changing, what this means. So actually, if you understand, it all becomes really simple. I said that on the midterm, you weren't yet there on that level to really understand everything. So try to think of it. This is my advice. Just play with it. What does this mean? If I change, can I apply to this case? Think of the limiting cases, always. And as an exercise, it's good to apply time binding to simple structures. To start with, simple cubic, BCC, we'll do FCC now. They're too easy to be in the exam, but your goal is not to pass the exam. If you study for the exam, it's not easy to pass the exam. If you really try to understand and play with it, I mean, you have to be a bit entertained, then you will understand and exam will be much easier. So don't be preoccupied. Okay. If there is no questions, I would suggest now to solve the homework on the blackboard. It's an easy one, but just to make sure that the whole class is following. If you're bored, I mean, for those for whom it's too easy, I mean, go for coffee if you want. I don't mind. I'm really not, I'm just doing this to make sure that the whole class is following and going forward. Because in the exam, in the final, there is 2 problems. And I don't know now what they will be. But usually one is time binding, electron. I mean, I'm not saying it will be, but it's commonly. And mostly you guys like it. Mostly it's like you're asking, will you put? But at this moment, I'm not so sure that you're all confident with that. But after a few problems on the blackboard, it really comes to finding the neighbors. And it's trivial to find the neighbors, so that's why I guess it's a very popular problem. So I will cancel. And I will hope that the volunteer will come to the blackboard. I have more homeworks for you. You want to come? Okay, let me see somebody else. No, wait, let me see. I know that you solved it. Not unique either. Did you solve the homework, William?
I was first trying to understand the last side.
Rabindra, did you solve the homework? Okay, okay. I'll also give you more homework. Oops, shouldn't give you these.
Excuse me.
Yes.
Will we also do some problem with multiple cases, not just one aspect? Like we did it qualitatively, but like solving the matrix and
I mean, we don't discuss the basis.
right now we are not discussing the basis.
Yeah, we won't be discussing the basis. I mean, it's changing the T,
we'll
the
just-
hopping terms,
yes.
and we don't really go into finding what T is. We won't come to find the numerical solution, exactly, everything numerical. We're keeping it like in parameters.
We just take help from CMP and just keep it up.
Just to get it in, this is a very basic course. Maybe you would like something more advanced. We had once a guy who said, but why are you teaching such easy things? When will you come to real stuff? I mean, it depends on the background, but this is very basic. This is to get an idea. And then in the next courses, for example, in the next semester, you will have a course taught by Ralph on the atomic structure. And they'll be doing much more things on the dispersions, on how to evaluate the ideas behind. Okay, I want to give you the homework. There are two sets of problems. I think there is one for everyone, I hope. But maybe there is one here missing. It's my copy, maybe. Maybe it's my copy. It's mine. Yeah, I think it's my copy. So on Monday we'll be doing the midterm in details, but we'll have time on this, at least half an hour, maybe even more, to go through problems. And I would suggest, well, whatever you want. Let's say what is for Monday. What do you prefer? To solve something on the lattices, a bit tricky, but on the lattices and the packing factor, packing fraction, or to go to a nice, and this is a nice but not simple problem on the tie binding, the bend, and this is nothing, this one. This second one here is done in 1 minute, if you see it. But I know that some people couldn't see it, so I put it, but it's 1 minute problem. It's actually from a quiz from Sandra, long time ago, but I saw some people having really trouble with that, so I put it for homework, but it's nothing, that's new. Well, you can decide what you want to do on Monday. For me, it's all the same. But do something, if you can, all together for Monday, that we can analyze. This one with the tie binding, it can be a bit tricky. It's not maybe easy to see. You have to expand. It's asked for you to draw the constant energy lines. It should be specifying a few constant energy lines in the, under the A of this problem. So you're finding isoenergy lines. You have to expand. So the first part around the K0 gamma, it's easy. But it's not easy around the W point. You try. You have to expand and play a bit. You have to notice a few things. That's a bit tricky. And in the other sheet, the first problem, it's, well, if you get it, it's trivial. If you don't get it, it remains difficult, but it's to visualize. I mean, the idea is to help you visualize. This is the problem from Sandra from exam, this one, and it was a bit tricky. I don't know how many people solved it in the exam. It can be both seen as very simple or tricky. So I don't know, depends. But it requires you to think of them, to visualize, and I think it's a great exercise to visualize things. The real lattice in the reciprocal space and what's happened. Good, Rabindra, you were coming to the blackboard. We didn't forget. Do I have this solution? I think this is it. So it's an FCC lattice with one s electron.
First there is 12 nearest neighbor atom. Nearest neighbor atom is at the location A/2. One is
The coordinates of the neighbors.
Coordinates of the neighbors.
From 0.
1, 1, 0. A/2, 1, minus 1, 0.
Well, you can put plus minus,
Yeah.
it's a bit faster.
All combination of this one.
Yeah, and also, yeah, okay, all combinations of the.
These are the coordinates of our dual nearest neighbors. Now the energy that will be to calculate EKS will be E atom.
Okay, so you are
Yeah.
starting from the final.
Yeah.
Yeah, sure, sure.
ES atom. We are considering only one S. And plus it will be phi S R this crystal potential ISR and plus summation e to the power I k dot r minus
Harriet, did you solve it? Did you try? Did you have time to try? I mean, it was very short time between Monday and today, but Tuesday.
minus
Okay, try. Do you think it's a bit better?
so for this we have to find this ik dot r. So therefore we have to find ik dot r for the 2-well sets. So if we calculate k dot r, it will be for this set k by 2 plus minus kx plus minus ky.
What was
All set of kx ki. It will be k by 2 plus minus kx
Okay,
plus
sure,
minus
sure.
k.
This is the hard part to understand. But then once you go to that, once you know what you're doing, I agree it's not easy to follow because it's in very general case. It's confusing with all the indices and everything.
For this, it will be bias.
I was hoping to, yeah, I was hoping to give it a bit today.
Bias.
This is pretty much that. I mean, you start from the equation. He is putting all the terms. I mean, in the equation, and what remains to find is the Hawking term. So you have dynamic, the crystal field, and the Hawking part. And the Hawking part is the one you will have to, which will have the k dependence, and which you have to evaluate. The Hawking part, yes. And it depends on that way, you see. The sum of the first neighbors, normally first neighbors, with the phase factor, and the Hawking C integral determined. And all you have to find is to find the vectors of the first neighbors and evaluate the phase vector, E on the IKR. This
And
one
that's
here.
vector will be this one.
This one, and this is what he did. And this is what I was doing with this E on the IKR on the graphene example, finding the neighbors. Here you have dependence. Here is in 3D. So it depends on the lattice. This is FCC. So it has the first neighbors in these locations, houses, and you just plug it there, and sum. I mean, it's easy to find the first neighbors. The sum is a bit complicated because there are 12 terms. Okay, so how did you put sum? When you sum all that, because we have a sum of all the neighbors, it's putting plus minus, no? This is a bit tricky. I mean, a bit.
So that's by symmetry, this all term will be equal, all 2 terms will be equal, and let us suppose it be T.
It's always the first neighbor.
This is equivalent to suppose T. This is all equal because it is phi s, this location is different, and by symmetry, rotation and deflection symmetry, the value will be the same.
With these two neighbors or these two neighbors, it's the same thing. Each of them sees the same world around, just rotating.
Like this will be better. So for this plane there will be 4 and this one 4, nearest neighbor, this is 4. All location at the location point given by this
It will
code.
have 4 terms. I mean,
Four
that's what
terms.
he means, yeah.
So
On
in
the
this Hawking term, integrating in this plane, the 4 of this plane by rotation and deflection symmetry, the value will be same.
Do you see this? I mean, This is the first step. If you can see the structure, this is like, I would say, more than 50% solved.
That is the problem.
Hmm?
That is the problem.
Oh, okay.
Drawing is not so good.
Well, we'll bring it to the blackboard next time to draw. It's really tough to
I'm
draw.
not saying that the drawing is not good. My drawing is not so good.
Your drawing, mine neither.
I realize that if you
Mine
see,
neither.
you really need to draw it, and I try to draw it, it's not going.
I agree. No, it's not easy. I agree. It requires a bit of practice. If you try it a few times, the simplest one, simple cubic, try with those, and then you go on and enhance the complexity. Complexity. Where we
Energy relation will be, it will be ES atomic, it will be minus, let's say this
The
term,
crystal field, yeah.
crystal field, let's say it will be delta V naught, and this term will also be the negative, because this is negative and this will be the positive, so negative T term, and we have to add all this phase factor over here.
yes.
So I take T common over here. So it will be e to the power I, k, x, let a dash be a by t.
This
I
is a
don't,
very simple thing actually, just a bit of mathematics to play with cosines. But really, the physics comes only in knowing this equation, in finding the first neighbors. That's the physics part.
And also the symmetry. I think that is symmetry. I think for this problem is
That you understand once. No, the symmetry, but I mean, you have to know if it's the first neighbors, you have a lattice. No matter if you look these two neighbors, first neighbors, or these two first neighbors, they see the same world.
Yes, but if we take, like, let's say P state instead of S, then we will.
Okay,
Yeah.
S state.
in case of S it is really, but in T we have to
Okay,
figure
okay,
it out.
true. No, I agree. In this case, it's really trivial.
Just I'm lazy, so I write a dash in case of a I do.
Yoi. I mean, it's fine for me, but I'm not sure your colleagues will follow all together.
Just replace a dash with a by two.
It's playing tricks.
Ky a dash plus e to the power I k x a dash plus minus I k 1 a dash plus I k x a dash y a dash plus I k x dash plus I k z a dash plus e to the power
Voila. Can you try to solve it? Okay.
So these are all 12 terms from this
I'm not
expression.
checking you. I have full faith you got it right. So now we have to expand on this cosines. Expand, just write in terms of cosines. Please don't do it. Don't write all these cosines. Go to the next step right away. I mean, it's.
No, it's we can take just the common from here, kx, a dash, and kx, like just from these four terms and change it into the cosine.
Exactly. So Joel, is it okay now? I mean, when you see the solution, it's not complicated.
No, I didn't do it that way.
You didn't?
Yeah.
I can hear.
So I didn't do it that way.
What other way there is? I mean,
I do it, I did it for the positive power and then I use symmetry and do all that.
Oh, okay. It's fine if you manage. Can I see? Do you have it here? You don't have it?
Like we have checked our final results about the width, it's the same.
It's the same. Really. Okay. I mean, it's better maybe to go the slow way, not to make mistake for that reason. Otherwise, it's. Yeah, I'm saying that this is a very easy. But if you don't get this one, something more difficult is.
There's too much rising.
Huh?
There's too much rising.
I agree. No. Also, in so much, I think it's easy to make a mistake also, but there should be some symmetry in the end.
So we can write these four terms as like this.
I mean, if you avoid it, you just draw the.
Kx a dash plus e to the minus I kx a dash.
You had this course, no? You had something similar.
E to the power I ky a dash plus e to the power
Can I
minus
remove
I
this
to
so that
the
it's not
ky a dash.
sorry.
Similarly, from other four, we can take similar common from this four and this four. So it will be plus to the power I kx a dash plus e to the power minus I a dash to the power I kx a dash plus
I'm really not checking at this level. I'll check the end.
kx a dash plus e to the power I ky a dash plus e to the power minus I a dash I kz a dash minus I kz a dash. So we can change this in cosine term.
Can you just go to the final solution?
Yeah. Now it is the final solution. T and it will be cos kx. We have to write an extra 2, so it will be 4 here. It will be 4 cos kx a by 2 cos ky a by 2 plus
I want this one.
a by 2 cos ky a by 2 plus this one cos ky a by 2 cos
You can never do the square. You can quadratic, so we can do for the
So this is our final expression.
Good. And now I want to draw it along gamma x. So gamma is 0, 0, 0.
So
and
ES k at gamma. So it is 0, 0.
0.
So in this case,
0, 0, 0. Yeah, in 3D.
yeah, 0, 0, 0. Sorry, 3D. We are considering FCC like this. So in this case, if we plot value of k at 0, it will be 1, 1, 1. So 3 times 4, it will be 12t. So it will be ES.
So in the exam, very often you get to plot these functions. Plotting part, even if you don't plot it perfectly, I mean, it's not so strict, but you have to have the right values. I mean, the maximum, minima of the band. So this what he's doing, it's really great. If they usually have, but usually there is something to plot. Maybe on the phonons, maybe on this time binding of electron.
So similarly, ESK for we take it at x point 2 pi by a 0, 0. So in this case, this will be all same. and y and z. This will be 1. This will be 1, but due to this, we have to put the value of kx as 2 pi by k. So it will be pi until b minus 1. So this will cancel out, and the remaining part is this one. This will be 1, and this will be minus 1. So it will be plus 4. It will be plus 4.
Okay, now you draw it.
Now,
So this line is, draw ES minus delta V.
so this is E. This is ES. E at ES atomic minus delta V.
Yes.
This is delta V, and this is the gamma point. And suppose this one is
How you draw it?
X.
I mean, this is the itself.
Yes, yes.
This you want to plot along gamma to x. So you plug the values of gamma and x points inside. Here it's x, this is x. You just have to put this for k values, kx, ky, kz. Yeah.
This is gamma point and this is X point. Look like this. I should write the coordinate. So in this point, this is minus 12, so we have to go down here. So this is minus 12 t at this point, and gamma x at x point it is 40.
There's 1/3 of this here. That much you can try to plot correctly. Not to make this 4 equally high as this is deep. So I'm not going to grade this in the exam, but you shouldn't make any kind of waves in between. It should be a simple line. But those who are more ambitious, they can easily see from here when it will give the value 0. For which value?
Pi value. At pi value. At pi value, the value is
Not in the
pi by
middle.
is
It's at here. I mean, it's,
Yeah.
if this is 360, it's 240. I think it was. I think I advanced the exercise. It's okay. I'm just saying it's shifted there. That I'm not grading, but this and this is grading. Don't draw a line. But as long as it looks like cosine, it's fine for the exam. I mean, that we understand that you understood that much.
so it
Yeah.
will be like this.
Yeah.
And the width is 16.
Exactly. The width of the band is 16. Thank you, Ram. Good. Okay, let's just first finish. I mean, we are done.